Hello everyone, welcome back to alkaline hydroxide 784, and today we are looking at complex numbers. Actually the topic is complex numbers expressed in Cartesian form. Okay, cool. So now I will just talk about the points, I'll just look at what points are there written next to that in the syllabus and talk related to that in a sense. Okay, so what are complex numbers to begin with? Well, basically, you know what real numbers are, right? They're like all the numbers, so just the numbers, I guess, like 3, 4, pi, 1.5154, whatever, anything that works in that sense. So how do you make a real number into a complex number? Technically, the set of real numbers is in the set of complex numbers, because real numbers are just the complex number without the complex part, where the I is 0. So if you've seen complex numbers before, you know what this I means, which is it is like the one of the real numbers. You know what I mean? Like if you have 1 in real numbers, in complex numbers you have I. And I is defined as the square root of -1, because for the positive numbers you can find a square root which is either positive or negative based on the way that the square root works. But for -1 you don't really have a number that when you times it by itself will give you -1. So they just came up with I to represent the square root of -1. So yeah, that's just how complex numbers came about. So what happens once you get this whole another infinite range of numbers in a different system? If you want to really show it on a graph, won't it be hard in a way? But for real numbers, you can do it with just one graph, like one line. You have the x-axis, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, for example. And you can indicate any number along that line. But once you include complex numbers, where do they fit in? They don't really fit into that real axis. That's why they created another axis vertically for the complex, the complex number. The imaginary axis, imaginary part. And that's where you have the I2, I3, I4, I5, I so on and so forth. But the real reason why it's actually represented like that, I believe it was mentioned in one video. I kind of forgot. But the oh yeah, if I remember to put the link, I'll put the link to that. But the idea is that basically, you know the the fact that we use the E equals the the sine and the cosine, that formula, basically something to do with that formula. So when you add in the I, it becomes like a 90-degree shift, and that's why it's represented like that in the axis. Yeah, so I don't remember the exact reason. You can go watch the video yourself if you want, if you're interested in further further learning, I guess. But that's not the important thing here. The important thing is that this is how the axis works. So yeah. So of course, now that we know that the axis is just basically an x and a y axis kind of thing, let's move on to how you actually use the numbers now that you know that they exist. So a complex number will have a real part and an imaginary part. So a real part will be like, for example, 1, 2, 3, 4, 5, that kind of thing, a number. And the imaginary part will be a number accompanied by I. If it's 1, then you don't need to really write that down, you just write I. And if it's 0, you don't write it at all. You don't need to write 0 I, you just don't need to write stuff. Yeah, that's logical. Anyways, so So when you put it on the graph, you had to find the real part. For example, if it's 5 plus 3i, you find 5 on the x-axis, you find 3 on the imaginary y-axis, and you plot the point there. And that's what you get for 5i. But actually, this is more related to the second half of this topic, which is the polar representation. So yeah, I will talk about that next time. More about it next time. So this time now I'll just focus on how you calculate with complex numbers and how you manipulate them and all that stuff. Okay, cool. So where do you find complex numbers? I mean, you're not really gonna be square rooting -1 anytime soon, are you? No, you're wrong indeed. In fact, they actually do appear quite often, especially if you're working with cubic or higher than that, like for those equations. For quadratic also it is possible, because if you have x squared equals to -1, you automatically get a complex root. You have plus and minus I, logically, and because of the existence of these numbers, you can now solve so many new equations, so many different new stuff, and that's great, right? I mean, if you refer to the joke about the math book having so many problems but no solutions, you make it happy by giving it solutions. Yeah, so yeah, anyway, that's not the point. So the point is, yeah, this is how they work. Yeah. Okay, so for slightly more complicated equations, which are just x squared equals to -1, for more complicated equations, it usually happens when you eventually end up with a factor that has a x squared and minus x squared plus something as your bracket, or so it actually ends up factoring into a pretty simple to easy to solve equation. Or else you probably will have a problem factoring it to begin with. If you cannot factor it, then that means there could be a complex solution that is a bit hard for you to get manually. And for quadratic, you can always use the quadratic formula. You know, the x equals to -b plus or minus square root of b squared minus 4ac, and the whole thing over 2a. Yeah, so that formula, it will help you find complex roots as well. It works with that. So if you're not able to factor the thing, you should try doing that if it's a quadratic equation. If it's a cubic equation and you can't even get to the quadratic factor, then I suggest you just use your GC and find out the answers. And same applies for higher powers, I suppose. Yeah, that's pretty much it. Okay, so once you get your root basically from doing a quadratic formula or something, because when you do the quadratic formula, you're likely to you might end up having a situation where your imaginary is in the denominator. But I'm not sure where it occurs, but maybe if you use your GC or something, you may get that. I don't know. So, or they may just give you a question where this kind of expression is given. So if you want to make sure there's no complex numbers, no imaginary numbers on the bottom, basically what you do is, for example, it's like how you try to resolve the surds. You know, if you have a 1 over square root 2, you just times it by 1 over, like square root 2 over square root 2, and you get square root 2 over 2, right? And likewise, you can do the same for complex numbers. So if you have, I don't know, 10 over I, which sounds very weird. Okay, 10 over I, then you can times it by I over I, which will be equal to 1, right? Yeah, and you will get 10i over -1, which will be in turn -10i in any case. That is the simplest form. But if you get something like that is like in surds, if you get something like 1 1 plus square root 2, for example, then what you would do, you would multiply it by 1 minus square root 2 or 1 minus square root 2, which is like the conjugate for the surds. And likewise in complex numbers, you use the conjugate. For example, let's just use the same kind of example. 1 or 1 plus I, you just times it by 1 minus I or 1 minus I, and you can resolve the I at the bottom. So when you do this, it's kind of like doing the a square minus b square thing. So in this situation, since I is actually going to become -1, no matter what you do, you end up adding the two things together. So for example, if you have 1 plus I and then 1 minus I, the result will actually be 2. Yeah, great. You won't get 0 because 1 squared plus 1 squared minus -1 is 1 minus -1 is 2. So you will get, that doesn't mean you'll always be getting a positive number down there. It can depend on the positive number down there. I kind of just realized. Oh well. Anyways, so you get a denominator down there which is real, entirely real, and on the top you can have your complex number without an issue. So that's how you deal with these roots if you need to. So just now I mentioned a conjugate, right? So basically, if you haven't figured it out by now, a conjugate is like when you have 1 plus I, the conjugate will be the one where the imaginary is the opposite sign in a sense. So you have 1 minus I. And in complex numbers, they like to represent it with this asterisk on the thing. So if they label a complex number as W or Z, for example, if they say W is X plus IY, then W conjugate, which will be indicated with the asterisk, is X minus IY. And yeah, that's important because they'll write like that in the questions. So if you see the asterisk, please be extra aware of it and use the conjugate. Don't use the actual W. You know what I mean? Yeah. So that's an important thing to take note of, so that you don't make careless mistakes in your exam. Keep your eyes open. Yeah. And it's not just for reading the question, it's also to look out for these symbols, like the asterisks, or I don't know, maybe if you're looking at vector question, you know, the bolded versus the non-bolded, that kind of thing. Yeah. Anyways, so the 4 operations of complex numbers. Okay, so you add 2 complex numbers. Well, that's pretty simple, adding and subtracting. It's like adding real numbers, so nothing crazy there. But multiplying and dividing, you treat it like how you would treat real numbers. Only thing, just keeping in mind that the I squared is -1. But when dividing, oh yes, this is where it comes into play. You can use the conjugate thing to resolve the complex denominator and make your life a bit easier, because dividing something that's not just I is gonna be a bit hard. But if the denominator is just 60, just divide it pretty easily, you know, because I squared is -1, right? So for example, you have 10 over I. If you think about it as 10, -10 times -1, so -1 over I would be I, right? So it becomes -10I. You don't need to do the whole conjugate thing to get to the answer, in a sense. Yeah, I don't think there's anything else much of, you know, major importance to take note of here, I guess. Just understand how I works lah. So I squared is -1, and I cube is -I, and I to the power 4 is 1. Yeah, just remember that and do things properly. And use your algebra skills, that's the important thing here. Equality of complex numbers. Okay, so when you say 2 complex numbers are equal, that means their real parts are equal to each other and their complex parts are equal to, imaginary parts are equal to each other. And you can be 100% sure that that's how it's gonna be, because in a way the imaginary and the real numbers are two different systems in a sense. So for example, if you have W is equal to 2 plus 3I, and you have a number z that is equal to w, which means that z must be 2 plus 3i. It cannot be 4 plus 1i or something like that. It doesn't work that way. So just take that into consideration. And yeah, and another way of looking at it is, if you look at the Argand diagram, the thing I was talking about at the beginning, the x and the y axis, if you put 2 plus 3i in that diagram, the coordinates first, and then you plot 4 plus 1i, obviously you get two different points, right? They're in different locations. So that means that they're not equal. So in order for it to be equal, it must have the exact same real part and the exact same imaginary part. Okay, cool. And of course you can use this when you're doing a question. There might be some questions that say this plus this is equal to this or something like that, and then you can use it to solve the equation. And the most important part of doing these kind of questions is to remember that the real and imaginary parts can be done separately. So you can say, balancing real parts and then balancing imaginary parts. It's like how in when you're doing your partial fractions, you try to find out the balancing of the x squared and the balancing of the x and balancing of number, for example. Like that, you would do balancing of real part and balancing of imaginary parts. Okay, so the final thing here is the conjugate root of a polynomial equation with real coefficients. Oh yes, yeah, this is a very important thing to take note of, because they like to test it. So they'll ask you a question that requires you to know this information. So basically, when you have, okay, let's start simple. You have x, so you have x squared plus 1 is 0. You know, the x squared equals to -1. So in this case, you don't have any complex coefficients. Both of the coefficients of the x squared and the 1 is just real. They're real coefficients. So in this case, your answer is plus or minus, right? You have you have that plus minus in front of the I, which means the conjugate roots. And likewise, for any polynomial equation with real coefficients, you will always have at least one pair of conjugate roots, in the sense. But if your equation has got complex coefficients, then it's not very likely to have the conjugate pair, in the sense. So when you are trying to solve equations where, for example, you have x cubed plus blah blah blah, and then you can look at the coefficients first and then see if there is a factorizable quadratic out of that. You can actually find out by looking at that, because otherwise you can just go straight to your GC and then type in the equation. If the equation has fully real coefficients, then you can actually factorize it into the quadratic and the linear factors. And the quadratic is the one with the conjugate root pair, and the linear will be the one which has another root, I guess. It could be a real or usually a real root, in the sense. So let's take that into consideration when you're doing the complex number questions. And next time we will look at more things about the complex numbers in the polar form. I hope you're looking forward to that. So I hope for now you at least know the basic way of dealing with complex numbers, the algebraic way of dealing with them, and how they work in a Cartesian sense, I guess. If you enjoyed this video and you found this useful in some way, then you can press the like button and subscribe. And with that, I would like to say thank you and bye.